In the previous tutorial, we explored the implementation and use of a DSP technique called correlation. We built both narrow and wideband filters using this simple technique. At the center of this technique was a reference signal we stored in an array. In this tutorial, we will explore some of the finer points of designing bandpass filters. While we have developed these filters from a perspective of correlation, the literature actually calls this class of filters finite impulse response filters. To see why, let's substitute our usual signal generator with an impulse generator. I've coded up an impulse generator here. Source is fairly simple, you can look at it. If we run this, we can see that each time there's an impulse, we get a copy of our reference signal coming out the correlation unit. Note, however, that the waveform has been greatly reduced in amplitude. The scale on this one is 0.6, the scale on this one is 10. Note also that we get a copy of the reference signal out and then the waveform goes to 0 and stays there. This means that if the input goes to 0 and stays there, eventually the output of the finite impulse response filter will also go to 0 and stay there. Now let me introduce a few new terms. What I have previously called the reference, the literature actually calls the impulse response, no surprise, or the filter kernel. I will endeavor to use these terms from now on so as to be consistent with literature. This type of function is so common that we will create a module to implement it. I'll call it general FIR, and we're going to package together a shift register and this dot. Here you can see my general filter. Here's what the code looks like. Here's my shift register. I make it the same size as the impulse response or the kernel. I implement my shift register using a rotate command. This rotates the Z array left one place or upward one place, and then in the 0th I put the in. Then I compute the dot product just like before. So I've implemented my shift register and my correlation. Let's turn now to exploring a few properties of these finite impulse response filters. Let's go back to our signal generator and our wide reference generator. Oops, I should call it the wide kernel generator. Our wide reference, our kernel, and our old signal generator friend. Now let's do a scan from fairly wide, nearly half the bandwidth, and we'll set a narrow filter, only one single frequency, and we'll do a run, and we'll see our familiar waveform. Now, it's narrow, like we expected, but its stop band is pathetic. Now down here on the left-hand side, we have some numbers which are actually markers, and we can set this marker to make some measurements. And we can see that this side lobe right here is only down about 11.5 dB. That's pathetic. So let's do a little exploration here. First thing we'll do is try to make our filter a little wider and see what happens. Now, here we find that the first side lobe is down over 20 dB. That's good. Notice here's our kernel. I show. This is this output right here. That's our filter kernel. Notice how it goes to 0 down here on the sides. Let's do one more here. Notice how now it's not 0 on the sides. And we'll see that our side lobe is bad again. Back around 13 dB. Make this a 7. And we'll see yet again the side lobes, or the ends of the kernel, are down towards 0, and the side lobes are much improved. So we've seen a pattern here, and we've seen that the side lobe tends to be better when these corners out here, the ends, are at 0. Now, we can force the ends of the kernel to be 0 by applying a simple function called the Han window. And I have coded up the Han window. And to see what the Han window looks like, we're going to set our reference frequency to be DC, or our kernel to be DC. And we're going to look at this output. As a reference. And we can see that basically it's 0 on the edges, it approaches 1 in the middle, and it's 0 on the edges. And if I pass this kernel shown here through the Han filter, we get a new filter kernel that looks like this. Zeros at the ends, basically multiplied by 1 in the middle. It's a scaled version of this. The Han window is called a raised cosine because basically this looks like a cosine function that's been raised above the DC of 0. So let's go ahead and use the scaled version, or the windowed version of our filter kernel. We don't need to see this anymore. Actually, we don't need to see this anymore. Now we can go and look at our output here. The Han window has reduced our peak output by about 5 dB, but our first side lobe is down now by 36 to 37 dB. So if I scale this, which I can do, to move up our peak, we can see that our first side lobe is down about 31 dB. This is much improved. Seeing that the Han window function is so effective, you might ask if other windows are more so, and the answer is yes. There are dozens of window functions. A few of the more popular ones are shown here in my next example. Popular ones are none, the Han function, which we just looked at, the Hamming window, which is a small variation on Han, and the Blackman window. Let's go ahead and run this simulation. Notice I have a fairly wide filter running here, so I'm going to have to scale this to see the edges. Now, we can order the performance of these filters by stopband rejection. The order would be none here, no window function. Here, would be the Hamming window. Here would be the Hahn window, and down all the way at the bottom is the Blackman window. However, this cursory examination might be inadequate. Let's look closely at this roll-off region. What we see here is this is no windowing function. This blue one down is the Hahn window function, which has a better stop band, but notice that the roll-off is a little slower and that there's this first side lobe, which is fairly large, down 40 dB from the peak. The Hamming window, which is this black line right here, has this first side lobe which is suppressed a little bit, and so it's down about 50 dB at the first side lobe and tends to stay relatively fat through the stop band. The Blackman window rolls off slower but has a substantially better stop band rejection of about 69 or 70 dB. This example emphasizes a common trade-off in filter design. Improving one characteristic often means degrading another. Compromise is the word of the day. There is an even more fundamental trade-off demonstrated by this example. Note the trade-off between the speed of the roll-off and the depth of the stop band rejection. In general, the better the stop band, the slower the roll-off. Please note that this trade-off is not universal. As might be expected, there are more sophisticated window techniques which provide deeper stop band rejection with steeper roll-off. A search through the literature will reveal a plethora of window functions. I encourage you to read up on some of these windows and try your hand at coding them and running some simulations. I'm going to close this tutorial with a nifty little trick. As you have seen, running scans to determine the passband can be a time-consuming process. Wouldn't it be nice if we could somehow feed in all the frequencies at once? Fortunately, there is a simple way to do this. You simply feed in noise. In this example, I've provided a random number generator which can be used as a noise generator. Let's see what happens when we use that signal. As you can see, you get fairly accurate results almost immediately. You let this run for a while and you will find that the scope traces are refined until they essentially match what we saw in the scanning technique. In this tutorial, we introduced the industry terminology of finite impulse response filters, impulse response, and filter kernel. We then examined the stop band and roll-off properties of the simple filters. In an effort to improve our stop band rejection, we introduced the principle of windowing and examined several of the more popular window functions, the Hahn, the Hamming, and the Blackman. We then took note that improving the stop band coverage came at a price. As a rule, as we improved the stop band, the roll-off characteristics of our filters was compromised. In the next tutorial, we will continue to explore finite impulse response filters and see how they can be used to implement a phasing type receiver.